Hi there, my name's Justin Stevens, and this is my video lab report for lab number 4 for Physics 2211. Alright, so a quick overview of the lab. In this lab we're going to analyze the motion of a weight which is on the end of a spring pendulum. We're going to determine the spring constant and use that to help model the system in GlowScript. In our model we're going to calculate the change in system energies over time. Which these energies that we're including are potential energy, kinetic energy, and spring potential energy. So the principles we're using in this lab, of course we're using Newton's second law, force is equal to mass times acceleration. We're also using Hooke's law, which is that the force of a spring is equal to the negative spring constant times the displacement of the spring. And we're also using the energy principle, which is that total energy is the sum of all the different types of energy, and like I mentioned earlier, we're only including gravitational potential energy, spring potential energy, and kinetic energy in our simulation. So here's the video of our the spring pendulum. We're given the mass of the weight at the end, which is 0.4 kilograms. We know the gravitational acceleration for Earth as 9.81 meters per second, and we're able to track the x and y position data of this weight in Tracker. We're also given the length of the spring as 0.7 meters when it's hanging with the weight on the end, meaning that when the force of the spring is equal to the force of the gravity, its length is 0.7. So when we track in this position data, we get these two graphs you can see on the right. The top is the x position over time, and on the bottom is the y position over time. So by analyzing the troughs and valleys of the y-graph, we're able to find the period for the oscillations in the y direction. And then by using the equation which relates spring constant to period, we're able to solve for our spring constant. And once we have that, we're able to solve for the rest length of our spring. So we get a spring constant of 6.83 Newton meters, newtons per meter, my bad. And we get a unloaded length of 0.123 meters for our spring. So when we go to model this system, we plug in the constants we know. So over here on the left, you can see that we plug in 0.4 kilograms as the mass of our weight, and we put in the initial position from our tracker data. And we assume there's no initial velocity. Over here on the right, we plug in our gravitational constant, and the spring constant and relaxed length of the spring that we just found. And then we calculate, basically, from our initial position, what is the stretch of our spring by getting the difference between the weight position and the spring's anchor point. And down here we calculate the energies based off of the initial conditions of our simulation. And when we do the calculation loop, we basically cache all of our energies. That way we can compare, once we calculate the new energies, to find the deltas for each one. And then we calculate the force of gravity acting on our weight, and the force of the spring acting on our weight. And we sum them to get the net force, and then we integrate that force into velocity, and integrate that velocity into position. Once we've updated the position and velocity of the weight, we calculate the new state of the spring by repeating the same steps we did for the initial setup. After that, we recalculate all of the different energies at play in the system, and then we sum them up to get a new total energy. And then we compare these new energies with the energies we saved at the start of the loop, and we plot the changes in these energies. And so the results of our model are shown here. You can see the simulation running over here on the left. The red shows the observation, and the blue is what the model is doing. Up here on the right are the plots of the changes in energies over the simulation. So you can see that even though all three of these other energies are oscillating, the total energy remains at a constant zero, or the change in total energy is a constant zero. And down here in the bottom right is our modeled position and our observed position. And so you can see they match pretty closely. And so what does it mean? Does our GlowScript model satisfy the energy principle? And yes, our model does. Throughout the model, the total energy remained constant. The change was 0, which means that conservation of energy was true for our simulation. And then how do the oscillation periods in the x and y direction compare? The period in the x direction is a little bit longer than the period in the y direction. So if you noticed in the model video how the weight as it followed its path sort of changed shape, that's actually because it's taking longer to complete an oscillation in the x direction, or to swing back in the x direction, than it is to create an oscillation in the y direction of the object. Thank you.